Okay, so now we're ready to talk about homology groups. Okay, so so if you recall, it's like we had this idea of cycles and boundaries, right? So denote this by BP of K, right? So this is the image of the P plus 1 boundary operator, and then the cycles are ZP of K, which are the kernel of the boundary operator. Okay, and we know that the boundaries are a subgroup of the cycles. And this sort of comes from the fact that the boundary squared is the zero operator. Okay. All right. So now we can think about what the homology groups are. So this is a definition. Right. The P homology group is the P cycle group. Okay, quotiented or modulo the P boundary group. Okay, and it's denoted by HP, right? So it's just the quotient of the cycles by the boundaries, CPK modulo BPK. And then there are what are called Betty numbers, okay? The P Betty numbers not just the rank of these groups. Well, the P Betty number is the rank of the P homology group. Okay, and that's denoted beta. Beta P is the rank of HP. Okay, so if you haven't seen the idea of quotient groups before, the essential idea behind what is an element of the quotient group, right, is the following. So, so every element of the quotient group has the form of, let's say, C plus BP, where C is in ZPK, and then BP is what you expect it to be. Okay, so basically what is happening here is that you take a cycle and you add to it, it's like the entire set of boundaries, okay? And you think of this as what is called a coset in this space, okay? So we say C plus BP is what is called a coset. Right? Of BP in ZP. Okay. So again, you should think of this at the level of sets. Okay. And what essentially happens then is that what this does is, in essence, to identify any cycle which differs from another cycle just by something which is in the boundary. Okay. So this notion of coset defines an equivalence class. this defines an equivalence class. And we say that C is equivalent to, say, C prime if and only if the difference is in BP. Okay? All right. And it's easy to convince yourself that this is basically saying that C is equivalent to C prime if both of them are in the same coset. Okay? All right. So you might ask, well, what is the meaning of this? Why do we care? All right. And the reason is because, we had said that the whole point of homology was to try to give you some sense of, holes, if you will. It's like in a space. So let me sort of give you an idea here. Okay, so imagine you have the torus, okay, and intuitively there are essentially, and if you're just looking at the surface, so it's not a solid donut, but it's just the surface. Okay, so this is basically S1 cross S1. Okay, so intuitively it's like there are basically two holes in the torus, one of which essentially goes this way around, sort of just one ring, and the other one which sort of goes all the way around. Okay, so these are going to be two generators of the one homology, if you will. It's like of a torus. Okay. So, all right. So the bottom line, if you will, is that you want to be able to identify this loop here with, say, another loop which is slightly shifted apart. Okay. And so you want to be able to say, well, this is this because we can sort of just move this curve along and nothing happens. It's like you haven't really changed anything. Okay. So this is exactly where this idea of a boundary comes in, right? Because if you look at, these two curves, they you can think of them as the boundary. It's like of something which is, this part of just the surface of the torus, right? So you can shift from one to the other. It's like by something which is the boundary of something which is on that surface. Okay, so the bottom line, if you will, is that I don't want to distinguish between these two loops because I can basically continuously deform from one to the other, and that's exactly why it's like I've quotiented by things which are which are boundaries, if you will. Okay, another way to sort of think about this is that if you're just in two-dimensional space and you have some sort of hole here, all right, and I have a loop around it, okay, which is in some sense it's like encompassing the whole. I could also have a slightly different loop, right, around it, and I want to think of them again as being related to each other or equivalent to each other. And they're equivalent because, again, there's this sort of annular region now whose boundary, right, is the difference between the two curves, if you will. Okay, so again, it's like this is sort of the motivation, if you will, of why I want to say that something is equivalent to something else, right? The two curves or two cycles are equivalent to each other if they only differ by something which is a boundary. Okay, so you might then ask, well, okay, how does that guarantee that I have or do not have a hole, right? So, all right, so let's look at the situation where there's no hole in the center, all right, and then I just have a loop like this. Okay, so now this thing here, right, is, so I mean, I would say that cycle is the boundary, obviously, of the shaded region, okay? And since you have the entire shaded region, right, which is admissible because, there's no hole which prevents me from, doing anything, right, then this thing identifies to the zero cycle because it is really just in the image of the boundary. Okay, so if something is in this space, it's like then we identify it. It's like with something which is trivial. Okay, and so this is not something I want to think of as a whole, right? I mean, this loop is not something I don't think of as being associated with a whole, whereas this loop I want to think of as being associated with a whole because there's no way to I could imagine shrinking it, but it doesn't shrink to nothing because there's this region which is not in the domain, which I can't shrink past, if you will. Okay, so anyway, hopefully that gives you some intuition. It's like for Y, it's this P homology group, which is the cycles modulo the boundaries, right, becomes then a way of describing the p-dimensional holes in the space. And again, it's like you want, it's like you want a region which is a cycle because you want to have some idea of, in some sense, enclosing or enveloping. It's like some sort of domain. Okay. All right. So let's move on. So there's some other things that's like we can say about this. Yeah, I guess I should also say that C, it's like equivalent to C prime is also referred to as homologous, as in coming from homology, right? They're related, they're equivalent in the sense of homology, so they're homologous. Okay, so the cardinality of the group is called the order. Okay, and since we're using sort of Z mod 2Z coefficients, if you have sort of n generators of the group. So as an example, if you're just looking at the chain group and you had n p simplices, right, then the p chain group will have 2 to the n entries, if you will, right? Has order 2 to the n. And that's because it's like for every one of the simplices, you can decide whether it's there or it's not there. It's 0 or 1, and then the n of them, so it's just 2 to the n. Okay. And then the dimension before I say that, yeah, so, and okay, you have 2 to the n, it's like order, and it is isomorphic to, okay, so there's another notation for Z mod 2Z, it's like, which is just Z sub 2, all right, so it's just Z2 to the n, okay. All right. So the dimension, if you will, of this space is referred to as the rank. Okay, and I denote that by n. N is equal to the rank of the Z mod 2 to the n thing, okay, which is the log base 2 of the sort of the cardinality or the order, right? So let's call it the order of Z2 to the n. Okay, so some observations, right? So we know that HP is equal to ZP mod BP, right? So the order of HP is equal to the order of ZP divided by the order of BP. Okay. Alternatively, it's like we can think of it in terms of the rank, right? So we know that the rank of this P homology group is what we've referred to as the Betti numbers. So beta P, which is the P Betti number, is equal to the rank of HP. Okay, and it turns out that this is equal to the rank of ZP minus the rank of BP. Right. So again, you can, it's like you can think of computing, it's like the Betty numbers in two ways, right? You can look at the order, it's like of this, it's like expressed in this way, and then once you have the order, right, you can relate it to the rank by taking log base 2, it's like of the order, right? Okay. So again, that sort of gives you sort of a high-level idea or introduction, it's like to this idea of homology groups, and if you will, it's like the Betty numbers again tell you the number of p-dimensional holes is like in the topological space. Okay, so let me just stop here for now.